But we're going to stream today because I managed to bring the power supply for my laptop. Battery is more like a UPS than anything else. But I can run some streaming virtual machines on it. So that was the goal. And it's got a 3080 in it. Because you need a 3080 in your laptop. In case you need to hook up a PC. All right. This is CPSC 416, in case you were confused. Today is October 31st, 2023. I don't know who I am, and I don't know why I didn't click on the Sunday. All right, this is boring, but it's still here. Logistics. Blah, 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 blah. Nothing actually. I just generate this by going through Canvas, and hopefully I did it right. But whatever's in Canvas is really official, and this is more of a reminder that there are self-assessments to do. There was no self-assessment for the Capstone discussion, so the self-assessment for the today's lecture last week was due a few minutes ago. We have regular classes next week. The following, there is no Tuesday class. That is the 14th of November. They're giving us Monday, Tuesday, Wednesday that week. There's plenty of things. There's a couple things later this week. You'll notice there's a lot of deadlines in here. None of them are too onerous. I just added this slide because I had someone got confused by this, and I swear that I've said this before, but like somebody today on Discord said, is there a rubric for the capstone? I'm like going, I forget to put the rubric up. I thought I put a rubric up. So I had to go and check Canvas and make sure that I had put a rubric up for all three parts of the capstone project. And indeed, I did actually put a rubric up. But then I could say, is there something wrong with the rubric? It is there, because of course I get to be a smartass answer back to somebody who didn't bother to go look. So yes, there is a rubric for the capstone. Capstone groups are self-declared until the deadline, and then I'll actually manually create real groups. To distinguish these groups from any other of the prior groups that were numbered, I used Greek letters. So if you think somebody said, I'm trying to get into group 26 or something, I don't know what number it was, and I can't move into it. And I was like, then that's probably because you're trying to move into the wrong group. So I used Greek letters, and it turns out that that was fortuitous. If you think that you are in a capstone project group and you think that it has something other than a Greek letter, then you're wrong. I only created 10 groups because that was about the number of multi-person groups I had last time. If those run out, just let me know and I'll create more, because there's, 22 Greek letters or something? I don't know. 24? How many Greek letters are there? How many of you read Greek? Monophonic or polyphonic Greek? Huh? What? Modern Greek is monophonic and ancient Greek was polyphonic. For some reason they added, and I remember this because in Windows they actually added support for polyphonic Greek. And I was like, how many dead Greeks do you really need to be able to use your Windows computer now? But somebody thought it was worth the effort to put it. Okay. Weekly reports for your capstone project are in fact individual contributions. They're not group contributions. You guys want to agree on some boilerplate to put into each of those, that's fine, but I still expect to see individual contributions, because I don't care what, I specifically am looking at your introspection, not your group's introspection. What are you learning from this? There is a rubric for the weekly reports. I didn't have, but I just simply took the things that I said I wanted to see in your weekly report and turned it into a rubric and assigned them any number of points. So there won't be any surprises there. We didn't have a TA meeting last week for some reason. Is that a holiday? I don't know why. We did have a TA meeting yesterday, and so the TAs have all been assigned weekly reports to review. Second weekly report was due 7 minutes ago. So they should be providing feedback on a fairly accelerated basis. I think I'm mostly caught up on grading. Surprising how much time it takes to grade things that I don't even have to look at. Canvas makes it very painful to walk through one at a time and do. If you think there's a problem in the grading, let me know. I will look at it. Implementation reports. Somebody said, oh, my group partner submitted the implementation report. I'm like, implementation reports are an individual contribution. You weren't given the same designs to review that your partners in your group were. So this was an individual contribution. I would say that one of the interesting things I found in going through all of the design project 2, I think it was design project 2 implementation reports is that I would say about 75 or 80% of them were, sorry, didn't have a lot of time. So I appreciate you guys prioritizing the class. Thank you very much. And then the 20% that were there, some of them were actually quite good. Some of them were off in the weeds, like people implemented other things. There were several people who submitted someone else's work. Now, I realize that it's kind of funny to take slides from a different class and submit them, but technically that isn't your work product. And so technically that is actually plagiarism. Not going to bust anybody for that, but please don't submit someone else's work and claim it as your own. It's just not a good habit. Today's failure is from earlier this month. There's a GitHub full of these things. Kind of cool. And it's actually still updated. So it has like 10 years worth of, at least 10 years worth of these. This was only a 4-hour problem, but it was an interesting problem in that it affected something that we all use, which is the domain name service. Have any of you ever heard of Cloudflare? Great. Okay. So one of the things that Cloudflare provides is a public-facing DNS service, 1.1.1.1. And they have a VPN service that's called 1.1.1.1 or Warp 1.1.1.1 or something. We'll use that because it is a very efficient, high-performance domain name service. They do a lot of things in order to optimize the performance of their domain name system work, not the least of which is they pull down and cache the contents of the root domain name servers, top-level directory servers, of which there are like 16 now. They're called very interesting names like A, B, C, F, G, H, I. Yeah. What they serve is a list of all of the top-level domains, .com, .edu, .org, .gov, .ca, so on and so forth. And that's hierarchically decomposed then. So they don't keep all of the domains there. What they do is they keep a list of who's managing what. So who handles the .coms, who handles the .edus, and then they send that down to the individual name servers that handle a particular domain name. And this actually can go ad nauseum, so you can go multiple levels deep. And the convention is that we have .com. So we use dot as a separator character to determine what the boundaries of this are. But Cloudflare actually caches the top-level directories, so they don't have to go and fetch information from them because it doesn't change very often. And they do it normally on a schedule of something like once a day or once every 4 hours or something. And on the 21st of September, a new DNS record type called a ZoneMD was actually added to the file. And I'm sure this has been proposed 5 years ago because changing almost anything in the DNS system, like adding a record type, is very rare. And I've been involved in adding some of the record types. There's a couple of types that we added for AFS. There's AFSDB record type, believe it or not. And in those days, you just send an email to Paul Makapetris and say, hey, Paul, can we add another record type? And it would just happen. Now, not so much, because it's this very large, decentralized, scale challenged problem. You look at it and you say, gosh, we should have a Paxos server for this, right? To replicate our DNS servers using Paxos. And they probably do use some sort of scheme like that. I don't actually know what they're using. Cloudflare, which automatically fetches and parses the TLD zones, top-level domain zones, didn't parse this new record type properly, and therefore it broke. So they stopped getting updated copies of the top-level domains. Most people didn't really notice because it doesn't change very much. You don't add very many top-level domains very often. But the cache versions had a lifetime. 4th of October from the 21st is what, roughly 2 weeks? Something like that. So about 2 weeks after they fetched it, they said, this is stale. Does that tell you how fast things change? Not very. And since it was stale, they stopped handling those correctly. They started rejecting those names. And in fact, it was actually DNS security that was rejecting, because it would no longer use the stale information to do DNS security validation. And what was, I really liked the blog post, because the actual blog post on this said they had a 12% increase in the number of failed top-level domain name lookups. I think it was because of the top-level domain. And I said, no, you had a 400% increase, because the background failure rate was 3%, and it went to 12%, or 15% actually. So they had, in fact, a 5x, a 500% increase. But 12% made it sound a lot less impactful. So you have to read these things pretty carefully. I should have put the link to the actual blog post in there. That's my oversight. And this immediately reminded me of one of my favorite XKCDs, which is our infrastructure of the internet, which is all of these cute little pieces, including, and I always love this one down here in the corner that says, a project some random person in Nebraska has been thanklessly maintaining since 2003. And this is not made up. This actually happens in the real world. People work on these projects because they're geeks and they like working on these projects and feeling like they're doing something useful. But then we build stuff on top of them. And it's really cool to look at the list of things that have broken, because the person maintaining them died, got a real job, stopped being funded, so on and so forth. There are lots of fragile components in this. DNS is one of the fragile components, and that one's actually more well-maintained than many of them. I've mentioned the network time protocol, which for a long time was one person maintaining it part-time. And you start reading about some of these open source projects where when they broke, it like destroyed a third of the of some particular domain, like I don't know, node.js. There have been a number of cases of things in Node that have broken and they stop distributing properly and things fall over. Because I guess people use node.js. You know, I am a systems hacker. There is only one language we use, and it's not JavaScript. What is the language? It's not Rust. That's heretical. C. We write in C. That's the one true language. If you're heretical, you write in C++. You write in Rust. If you're really old school, you write in assembler. Well, operating systems used to be written in assembler. Honestly, it doesn't make much difference. Probably wouldn't write your operating system in Python. But C is kind of like juggling with knives. Sharp ones, really sharp ones. And sometimes they go through your foot. Have any of you ever actually programmed in delightful language? It provides you with absolutely no infrastructure or support and allows you to do things that you should not do unless you really know what you're doing. And the problem is you might think you know what you're doing, but let's talk about Petrov, chapter 11. We were having a nice little conversation before class about this. That it's been interesting going from Kleppmann's discussion about replication and consistency models and Petrov. They aren't in the same order in the book. They're similar, but not exactly the same. And I like that contrast. I think it's really interesting. So lots of things in this section. There's a lot of useful information, but I don't really expect you're going to remember all of this. I think that there are some important things to take away here, not the least of which is that Petrov actually does a really interesting job of pulling out strong eventual consistency. Kleppmann doesn't do. That's an interesting takeaway from that. The two together do a nice job of playing off back and forth against each other. So hopefully that will help reinforce your understanding of what is really a very important topic in distributed systems, and that is, how do we keep multiple copies of things? And one of the things that I kind of glossed over before is when we started talking about Paxos, we talked about replication protocols, we talked about consensus. One of the things I didn't talk about is, when do our replicas become up to date? Because see, Paxos doesn't actually update the replicas. Paxos linearizes the messages. And it gives us, in fact, it gives us a serialized version. It gives us a log. This is a serialized version. We might have other logs, because these are linearized operations, we might have other logs that reach the same outcome, but have to apply the change to the database, because now we make it back into a key value store. So you do a get from that key value store. Okay, well, the Paxos people have decided, but nobody bothered to tell me, and I'm the one who owns the data. You know what the simplest way to do this is? Make the proposer, the acceptor, and the learner, because the learner is in fact the replica, make them all co-resident. Put them all in the same box, because then the learner instantaneously knows when the decision's been made. But even that isn't quite enough to solve that problem. Why? Well, what happens if I'm the client and I ask a replica that hasn't been caught up yet? So we talked a lot about catching up leaders, but we didn't really talk much about catching up replicas. And so one of the things that's good in this section is that Petrov talks about how you catch up your replicas. How do you make sure that you're giving the client the most recent version of the data? Well, one simple way to do this is to build a strong replication service, like Atomic Broadcast, which is basically a transactional mechanism for making sure that it's an all or nothing switch. Either everybody gets this outcome or nobody gets this outcome. Why don't we do that just as a matter of course? What? Inefficient. Well, it depends on what your definition of efficiency is. What is the definition of efficiency in your model? It takes forever to do this, right? You can't get anything done because we've now taken one network communications and said, we're not going to proceed until everyone has received and processed that request. Everyone, 100%. And so the interesting trade-off, and the thing that both Kleppmann and Petrov talk about is, how do we do this in a way that doesn't make our replication suck? Because bottom line, if we sit there and we wait for everyone to replicate everything, it's not going to be very fast. Now, here's the interesting question. Do we need that kind of consistency? Do we need to have that sort of strong safety guarantee? Maybe. This is one of the things that makes distributed systems hard. The correct answer to these things often depends upon the scenario in which you are implementing the solution. Did anyone in here take 313? Do you remember conversations about coherency protocols? You know what? Coherency protocols are exactly the same problem. If you think about the fact that we have to worry about what's cached in each processor core, that's in essence a replicated database. It's supposed to be identical, but what we learn is actually don't really need to be that strict about it because it almost never matters. Because 99.999% of the material that you are referencing or accessing is only of interest to you, to that one process, that one core. Things start to get interesting when you have multiple cores sharing common data structures. But even there, most of the time, there's lots and lots of stuff that isn't shared. Stacks and threads are not shared. So they can live in one core and not be hashed by anybody else. But if you send we'll go to C, you send the address of a local variable on your stack to another thread, it now refers to that. Okay, fine. Do you need strict consistency for that? Maybe, but probably not. Because I know that when I write code and I pass a parameter to somebody else, I don't change it while they're using it. Right? So I just structurally don't need to do that. Same thing ends up happening here. Most of the time, we don't need that kind of strong consistency because it just doesn't matter. I'm working on my own data, you're working on your own data. We don't need to rendezvous and synchronize that stuff. And so we're trying to strike that balancing act. When does it matter and when does it not matter? Now, it's really easy to say things that are causally related. It's easy to say these matter. The order of these things matter. I need to make sure that I'm seeing something consistent when there's a causal relationship. But if you change your key and I change my key and she changes her key, I had to actually look and find, like the two women class. There's no ordering. There's no causal relationship between. But if I read his key and I add the value of my key to his key, now there is a causal relationship. There is an ordering. When there's no causal ordering, the order in which his right to his key and my right to my key and her right to her key happened don't matter. That's why we have linearizability. Because in a linearizability system, we can actually say, well, his went first, mine went second, hers went third, or hers went first, his went second, mine went third. But the outcome was exactly the same, so it doesn't matter. Paxos will give us something stronger than that. It's going to give us a serialized order. So we take this thing, we shove it through this serializer, and we get a log out. Because a log is a serialized structure. And it says, hers went first, his went second, mine went third. We spent a lot of machinery in order to come up with this serialized log. And it didn't matter. There was no reason we needed to do that. When you look at Paxos Made Simple, Lamport describes a form of sparse serialized log. Remember, he has no-op commands that he fills in slots that he doesn't know what's there, and he reproposes the values and uses slots later in the log. So in fact, he's choosing a serialization of the possible linear logs. PMMC uses a dense log, and it insists everybody has to have the same entry in the same location in their log. So they both end up with logs that are identical. Then you go look at Raft, and if you actually haven't noticed, because we didn't really talk a lot about Raft, if you go look at Raft, Raft doesn't have a serialized log. It has a linearized log. It insists that we have a linear order. In other words, the outcome is the same regardless of the way, the order in which we perform the operations, but it doesn't insist that they have to be identical. They are isomorphic. Why do we do that? There's no reason to make people stop at a stop sign when there's nobody else on the road. We need serialization when there's potential for collision. When there's no potential for collision, it doesn't matter. And there's no reason to pay the cost associated with making you sit at a red light for the next 20 minutes. Anybody ever been to Bangkok? I have been at a red light for 20 minutes. We finally got out of the taxi. We were in a taxi. We finally got out of the taxi and went to, there's a SkyTrain type thing there, and got on that instead. It was literally not moving. There's nothing, there's no benefit to that at all. Well, in that particular case, it was gridlock. But if there was nobody on the road and it sat there for 20 minutes, you'd be like going, I think this is broken. But I'm one of these rule-first people. So until that turns green, I'm not going to go. Right. That's not the way the real world works. The way the real world works is we want to do things as fast as we possibly can. So back to the consistency models again. I mean, I've already been touching on this. What are the challenges in distributed systems consistency? Oh, and I got Dolly 3 to generate that image because I can now. And it's way faster and easier than me sitting down and trying to do that in Illustrator, which I could do, but it took like 2 minutes to do that. Have fun at the party. No worries, have fun. That's all right, I'm missing the Halloween party for the Cystopia group too, so that would be Margot's group. So we have to worry about network behavior. You know, drop packets, reordered packets, arbitrarily long delayed packets. And we're going to fix that because we're going to put timeouts on things. We have this consistency versus availability trade-off, and that's not a binary trade-off. It's kind of presented initially as if it were you have to choose one or the other, but then we start to like poke at it and we go, well, you know, I can give some consistency concessions and get better availability. Partitionability, you can't. You either handle or you don't. That one is sort of, the whole cap theorem thing is kind of a misnomer because you either handle partitionability or you don't handle partitionability. Transactional systems don't handle partitionability, right? If everybody can't talk to the coordinator, you're done. Oh, and that last point is what I started talking about, which was, when do we update our replicas? How do we get our replicas of the data to converge? We've got a consensus protocol now. We've solved all the world's problems. No, sorry, you haven't. You solved one problem. And it was really hard to wrap your head around that. And now I get to come back and whack you up alongside the head and say, well, you thought that was all you needed to know, but it's not. You still need to get those changes into your database. So one of the important takeaways from here, from Petrov, is he does actually say, how do you ensure that you give a client the most up-to-date copy of the data? You do a quorum read. That is it. You do a quorum read. Now, in fact, Petrov, just like pretty much everybody else, sort of conflates quorum with majority. And if you have a single organizational system, not a matrix, right? You know, 50.001%, and you win. You've got a quorum read. We know from our conversations there are ways of organizing things so that you don't need 50%. What you need is to have a quorum. And this becomes important, and Petrov does go into this, in data centers. Remember I talked about using columns and rows. So when you're building a quorum in a multi-data center system, if you can get everyone in your data centers to agree, so at least one node in every data center agrees to the outcome, and then one entire data center agrees to the outcome, you have a quorum. And that's not a majority quorum. It is, in fact, a quorum in the matrix. Well, here's kind of cool thing. When you go to read that value, if everybody in your data centers agreed on the outcome of the operation, you'll have a quorum. Because there's no way that anyone else, modular the way it's organized, but there's no way that anybody else could have a more recent value than what you're seeing. Because if you take all of your entries out, there's no other subset that reaches or achieves a quorum. You can read about that and go, that's actually kind of cool, isn't it? If everybody in my data center has agreed on what the outcome of that particular proposal was, then I know what the latest value is. I can break that. Jagged matrices don't work very well. You kind of have to have the same number of your data center. But let's not go down that path. It doesn't matter. The point here is you can do a quorum read. But what's the problem with that? Well, now that means in order to answer the client, to give them a strong consistency guarantee, I have to read more than one copy of the data. Back to the slowest link is going to define my performance. And for those of you who are working in a group, probably know that there's always a slowest member of the group. Maybe that's you. I don't know. Nothing wrong with that. It's just the reality of the situation. So Petrov does talk about the fact that you can compromise on this. You can say, I'm willing to do different subsets of this because now I'm balancing consistency against availability. If I read just one of the replicas, odds are I probably am going to get the current up-to-date copy of the data, but maybe, just maybe, I'm going to get a stale copy. So we talked about consistency models before. Petrov goes through the same list of consistency models. He does actually add session consistency as well, which is kind of interesting. In essence, it becomes, what is the client's perspective on this? What does it look like from a single client's point of view? The session, the state of that particular client. So consensus protocols provide us a linearization of the operations. We can then turn that into a serialization. We build a log. So we can build a log of these things and agree this is the order in which things happened, and everybody's going to see exactly the same order because we're shipping the log around now. We're replicating the log. That's what Paxos and EMMC and Raft all do. Actually, Raft does it logically, not physically. The data replication is not defined by the consensus protocol. So what I'm just telling you is the big lie I sold you, Paxos will solve all your problems. No, it solved a problem. You still will have to have a mechanism for replicating that data. And when you look at that problem, it's eerily similar to the how do I catch up the leader problem. Because I need to make sure that I've applied all of the updates, all the previous proposals. Have I seen everything? Have I implemented? Is it now applied to my database? It's not, do I have a copy of it locally? It's, have I actually applied this copy to my database, my key values? The consistency model that we need to use depends upon what the needs of the client are. The stronger the consistency model, the harder it is for us to make that perform really well. So often what we try to do is convince the customers that they don't really need to have a McLaren. You know, maybe they can do the same job with a Honda. You know, very expensive cars. I don't know, how many of you have McLarens? It's UBC, never know. Actually, I live in a nice building that used to have a lot of really high-end cars, and I don't think I've ever seen a McLaren in a garage, but I've seen lots of AMG, Mercedes, 7 Series BMWs, and Maserati, kinds of things that you just drive every day to and from school. Maybe really fast, strong, consistent budget. Maybe you something other than handmade leather interiors. Okay, fine. And guess what? That's what most people end up doing. And that's what most of the people are perfectly willing to settle for. All right, I don't really need to go from 0 to 60 in under 2.4 seconds. If you've never driven in the US, there are places where that 0 to 60 speed thing, which is 96 kilometers an hour, from 0 to 96 kilometers an hour. It's important because they put stop signs at the end of the on-ramps onto the freeways. I don't know why they do that. They do it. It's really important there. Maybe you're willing to pay for it there. Here, we give long stretches where you can speed up and flow into the traffic. You don't need a really fast acceleration. Do this with a Kia. But you got to be cool, so you're going to do it in a Tesla Model 3. We replicate for fault tolerance. Right, what does it mean to be fault tolerant? It means that we can handle some level of failure. Why do I talk about failure? Because we design to handle some level of failure. Last term I used Marvin the Martian blowing up the Earth. We do not normally build our replication systems to handle that particular type of failure. So it's important to realize some level of failure. If you're willing to spend enough money, I can protect you against the destruction of the Earth by Marvin, but probably not from a detonation of the sun. I'm not personally worried about that particular level of failure, right? It's sort of like, what do you do when the end of the world is coming? I don't know, grab a drink. Smoke a cigarette that's going to kill you 20 years from now. Because it doesn't matter. Right? The point is there are failures you cannot handle, and you need to be very clear. This is what I handle. Everything else, you're on your own. There will be some failures that will happen that you never even imagined, and you can say, that was in the bucket of things I don't do. And somebody will come along and go, well, actually, this is happening in the real world, and I need to pay you to fix it. And so you'll go back and you'll redesign, or you'll add functionality to your distributed system to handle a model of failure that you didn't previously think about. Oh, yeah, that's kind of cool. Job security. And you get to charge them for it. It's really easy to say atomic update is the way you want to go, because that provides you with this super strong consistency guarantee. But now we're back to transactions again. And transactions end up not scaling very well, because you have to get everybody to agree. And when you're just trying to decide on where to go to dinner, if you said, we will only go to dinner when everyone agrees on one place, the larger the group, the less likely it is you're ever going to get to dinner, and you will probably starve. So we don't want to build those kinds of systems. Small groups, you can get away with this. As the group size grows, the problem tries to scale out. This becomes less viable. People who need incredibly high uptime and rapid recovery of failing systems pay tens of millions of dollars for computers that will handle those failures. There is a company called Hewlett-Packard Enterprise, HP, that purchased a company called Tandem 15, 20 years ago. I worked with people at Tandem. They still sell the same computers, or the same basic type of computer at HPE that Tandem sold 25 years ago, which were hardware replicated systems that a single failure of a single component, you wouldn't even know. You have a red light that goes on somebody's dashboard that says you got to replace that. Buys this. Well, it turns out a different company I was involved in was working with one of the largest, at the time, they don't exist in a business, one of the, not because of the computer system, one of the largest financial market makers for US Treasuries. US Treasuries are US debt security instruments, and there's a huge number of them, like $35 trillion worth of. They made roughly 1/4 of the entire market in these, so that if they were unable to provide trading services, that it materially affected the liquidity of the US government. And so as a result of that, they had a requirement that if their services became unavailable for a period of more than 4 hours, they had to actually inform the Secretary of the Treasury in the United States. And do you want to be the tech guy who has to call the Secretary of the Treasury at 2 in the morning and say, I'm sorry, sir, but our systems are down? And the trading on these things is 24/7. Those are the people who buy these kinds of systems. They spend a ton of money. Another company that I know that makes systems that are similar is called Stratus. As far as I know, Stratus is still around. Stratus used a software fault tolerance system. Tandem, now HP, used a hardware fault tolerance system. And they were able to handle amazing failures. In Stratus, one of the things they would do is, like, if, let's suppose there was a panic in your kernel, they would actually rerun the operation on the next processor. And what they frequently found was that rerunning the same instruction, the same operation, would lead to a different outcome. We called them Heisenbugs. There were subtle timing issues that would just not happen very often. And so by switching over to the secondary copy, or they did three copies, tertiary copy, they were able to keep going. I use one computer when you can use 3 that are talking very, very quickly, very rapidly, trying to keep constant sync. So one would move forward like 25 microseconds, and then the next one would move forward 25 microseconds, and then the third one would move forward 25 microseconds. And then if everything worked, then you go back and you just keep doing that. And when one of them failed, they would try it on the next one. That failed, they tried it on the third one. That's strong replication. Really strong replication, down to like instruction level stuff. Super expensive. You don't really need that on your gaming rig. You might want it on your gaming rig, but you don't really need it on your. You don't pay for it. So the important thing here is to realize that often we can have relaxed consistency semantics here. And it's very similar. There's a network issue. That would probably mean the stream has broken. Oh well. It's being recorded, so people can watch it on YouTube. There's this register model that Petrov talks about, where you have safe consistency, which is kind of the opposite of what you think of as safe. It returns some value within the allowed range. Hi, this is a 64-bit number, so it's somewhere between, minus 128 terabytes and plus 128 terabytes. Okay, great. The regular kinds of memory returns the last completed write value to it. That gives you some sort of ordering on write operation. You know what you're going to get. And then there's atomic, which means that the value is instantaneously available everywhere in all of the caches on the system. And that's really strong. So this one, regular, means you get the last completed write value on this copy. That's what we're probably going to provide in a lot of cases, because it turns out that's enough. Consistency models, again, Petrov goes through them. They're basically the same. I don't want to spend a huge amount of time on this. I just want to point out, Putman goes through this. I've gone through it. Now we've got Petrov going through it again. But consistency is consistently one of the hardest things for people to wrap their heads around. And every time I go back through this, I end up going back to first principles and trying to make sure that I still understand it, because I do understand it, but by golly, it's not intuitively obvious. And I've been doing this for a long time. So if you find this confusing, it's not surprising. You have to keep going back and saying, oh, right. So somebody posted a video today talking about linearizability versus serializability. A log is serialized. A collection of logs that have the same outcome are linearized. Causally unrelated operations have lots of different orders that can be applied in. The logs that all work are linearized, but there's potentially more than one of them. Strict consistency means we have atomic writes. I write something, it's instantaneously visible everywhere. Well, all right, it's visible everywhere simultaneously, not necessarily instantaneous. It could be next Tuesday, but everybody will see that value next Tuesday, and nobody will see that value until next Tuesday. It just took us a while to coordinate that switch over. Linearizability is eventually everybody gets to see that, but non-causally related changes are not ordered. Sequential consistency means that for a single process, i.e. only the causally related things have strong order. Causal consistency means that operations that are causally ordered across processes are now ordered. Session consistency. Oh, and I have this nice little point here about vector clocks. So in a vector clock situation, what we end up doing is keeping track of the flow of the messages through the system, and we say the time over on that node was this in this vector. I don't know what it is right now. I know that when they sent this message, it was this. And so I can reason about kind of sort of what it might be right now. But I don't really care what it is right now. I only care about what it is when this message was sent, because I haven't seen anything beyond this, right? So if I see messages out of order from a single node, I can detect that pretty easily, because they're going to have, I'm going to look at their clock values and I'm going to go, okay, my timestamp on this is in the opposite order of the timestamps from them. So they sent it in one order, I received it in the other order. I can detect that. I can see order in which I observe things versus the order in which they performed them. Session consistency is client perspective ordering of operations. Eventual consistency, and I am hand-waving through this very quickly. Petrov goes into greater detail on this. I would recommend, if you haven't already read the Petrov stuff, read through it. It is saying the same thing, and we're going to keep saying the same thing because, my gosh, these are all very similar, aren't they? You look at them and you go, this seems kind of similar. And then you end up having to sit down and figure out that, well, except that in this case, this defines a specific ordering, and in this case, I've got 3 or 4 orderings I could see, even with just a couple of operations. Eventual consistency, which is one of my favorites, which is if nobody sent any more messages, eventually everything in the system would converge. Or as I've also heard it described, is never consistent, but in the limit it is. So when we're all dead, it'll be consistent, but we won't care. As strange as it might sound, eventual consistency is what we tend to do most, because it's the most available. It's very fast. In most cases, enough for us to get the job done. I think it's really cool. Every time I sit down and start looking at eventual consistency, and specifically I look at CRDTs, the way that they use lattices isn't about eventual consistency. So the interesting thing about eventual consistency is it's linearized. You look at it and you say there's lots of different paths through this graph, the order in which the events occurred. There's a lot of different paths through this graph, but they all end up coming out with the same result. And that's why eventual consistency, even though you cut through the graph at one point, you realize that the replicas aren't exactly the same, but eventually they will be. And we can make that happen. That's the point of CRDTs. Tunable consistency is sort of an interesting one in that, and this is not uncommon either. You see databases that say, this is how much consistency I need. You can turn the knob up and say, I need really strict consistency. You can turn the knob down and say, I don't really care. Send out yesterday's crap. I don't really care. Nobody's going to notice. And the big difference there is performance. For consistency, you're going to find that over time, your performance is lower than the weak consistency. So you do this because the weak consistency model, kind of weird. This is your McLaren, because it's going to go really fast. But I don't know, wrap it around a tree more easily, I guess. The analogy is kind of breaking down at that point. That's fine. We'll move on. Strong eventual consistency is something that Petrov goes into, and I think it's interesting because he says, he presents this as a middle ground between strong consistency and eventual consistency. So he allows some divergence, but then he adds some extra state in there that says, if you need strong consistency sometimes, but you're okay with eventual consistency the other parts of the times, here's a way you can achieve that. And in essence, it means if I need safety, I can pay the price there. But if you don't need safety, you can run fast. This is like you get the all singing, all dancing version. It does everything that we both need. Doesn't this sound like a marketing thing? Well, it probably is to some extent. There are a range of trade-offs here. So we've talked about making these design decisions, and it turns out that sometimes you can give people tunable knobs so they can change these design decisions. And this is very common. Redis, for example, I know has a variety of different choices. You can say, I need this level of consistency from my database. And it will give you that level of consistency, and you will pay the price if you're asking for strong consistency, and you will get performance if you're asking for eventual consistency. The cool thing about CRDTs, conflict-free replicated data types, C, ignore the F, RDT, because I don't know, I guess they didn't like CFRDT. These are specific operations that are composable and result in the same outcome regardless of their ordering. More recently, 2019, there was a slightly different take on this called MRDT that uses a different mechanism for achieving basically the same thing, eventual consistency using data structures that have specific properties. Redis uses CRDTs. They preclude conflict. So if you can't have a conflict, then the beauty of it is you don't have to worry about causal ordering issues. Sounds too good to be true. Of course, what you're disallowing are certain kinds of systems by choosing to limit what you will support. Okay. Do that in the name of performance. How far can we get with this? It turns out you can get really far. One of the fastest scalable sharded key value stores was built by the same group that came up with CRDTs in the first place, and it's called Anna. And it was, at the time they published the paper, the second fastest key value store available. The first fastest was one that was implemented using NIC cards that directly accessed memory on the computer. It bypassed the CPU entirely. And that was called KV Direct, and it was a Microsoft research project. And they were able to get 150 million keys a second, I think, per node. The numbers were just insane. But the NIC directly talked to the memory on the computer. It's like you didn't even need the CPU. So that was super specialized. Whereas Anna is just a piece of software. And they use CRDTs in order to build this replicated key value store. And Anna's out there. The source codes are publicly available. I think I saw somebody make changes to it recently because I have it watched on. But it's an interesting key value store. They don't require strict ordering. You have to have side effect-free operations. They need to be commutative, and the operations need to be causally ordered. Make all of this work right. But it works. And so it's a really good discussion. I don't expect that you're going to remember all of this. I do want you to remember the consistency models, because I think understanding consistency models is an important part of knowing what the tools are in the tool chest. But I don't expect you to know every tool in the tool chest. Petrov is the kind of book that if you end up working in this field, you will go back and read 2, 3, 5 years from now. Because Petrov is talking very practically. You might go and read Klutman as well. Klutman is a little more on the academic theoretical side. Petrov is more on the implementation side. But the two of them together really do a nice job of covering the range of options here. These are things I would expect that some of you will be dealing with in your Capstone project. You don't have to. Somebody suggested they were going to implement MapReduce. Like, okay, but why did you pick the tool before you picked the problem? And I will suggest that to you. It's really cool to look at all these tools. It's like, anybody ever heard of a Bloom filter? Bloom filters are this really cool probabilistic data structure that you learn about, and then you spend the rest of your career trying to find a place to use it. It's pretty cool. You know, it's like you hash to a value and you put it in the Bloom filter, and so you can take a value and you can look the hash up of a new value, and it will tell you whether or not that key is present. They use them in key value stores. Is this key even present in the database? Because if it's not in the database, there's no reason to go look. You can return the error right away. Haha, great. You can get false positives. You might have to do the full lookup, but getting rid of the true negative cases up, because you eliminate a whole host of I/O and a whole host of processing. Pretty cool. Great data structures. You look at them, you go, oh, so cool. And then you go, what am I going to use it for? So when you're thinking about Capstone projects, you should be instead saying, what problem do I find interesting? If you want, build Paxos. Take an existing system and I don't know, model it or something with it. That's fine. Those are all great things. But find a problem you want to solve. That's really the best technique, because that's what we do in distributed systems. People come to us and they say, here's a problem I want you to solve. And then you say, I could do a really clever job of that. The lunar data center. Somebody got $5 million to design a lunar data center. That could have been your money, because you could have sat down and said, I can make this work. This is how I'm going to design my lunar data center. And now, instead of saying, I have a sonic screwdriver and I need to find out where to apply this sonic screwdriver, you can say, I have a problem and I have this tool chest of things that I kind of know a little bit about, and I'm just going to reach in there and try and pull a few out and see what it looks like when I apply them. Because that's really where the interesting learning outcomes come from. Because you're going to look at problems over and over and over again. You may only use that sonic screwdriver once in your life. Don't memorize the sonic screwdriver. Learn how to analyze the problems, and then rustle around in that toolbox. And then you're going to pull a tool out, and you're going to use it, and you're going to say, this tool really was great, or this tool sucked. And you'll put it back in the chest. And you'll remember it when you have to solve, you come up with another problem that's kind of similar. And what you will learn over years of working in this business is the problems are always similar, but not the same. And so the tools that you use to solve the problems will very much depend upon the problem that you are trying to solve. That's why when you're trying to find something to do in your capstone, rather than pick the tool that you want to apply first, try to pick the problem you want to solve first. It's really easy to say, I want to use that really cool shiny widget. But I don't think that's where you're going to learn. But that's me. Convince me otherwise. That's all I have. Does anybody have any questions? besides him. Go ahead. He's not sure if this is a question. So the question is this a question or not? Okay. Right. So generally, things that involve money want strong consistency. And the reason they want strong consistency is because you don't want the money to show up twice and you don't want it to disappear into the void. I mean, it's sort of like that Bitcoin you mined last year that you had on a cold wallet, and now you can't find the cold wallet. It's gone. It's like losing change in the couch. You're never going to find it again, or it falls out of your pocket, right? Yeah. Banks don't like that. Banks want their ledgers to balance exactly. When you are in that kind of a strict environment, that's where, and it's the money people. What I was talking about, Lehman Brothers, who's dead, by the way. They crashed in 2008. They were the company that did like 24% of the securities market. They care. They'll spend the kind of money necessary to get strong security. You, with your iPhone or your Android phone and the pictures that you're storing in the cloud, you don't care if it gets replicated now or in 20 seconds. It doesn't matter to you. Propagate through the system. Hmm? So is your question, could I have different APIs that provided different service guarantees? Yes. That's a great question. Is that what you're going to do in your capstone? Because now you have an interesting problem. You have an interesting problem, which is, how do I distinguish, rather than, so I was talking about, you tune the knob based upon the whole database. You're saying, could I do this on a per transaction basis or per operation basis? And I don't see why not. It would be interesting to see what a system like that would look like. And so if you're looking for an interesting capstone project, sure. I don't know what people have done in this area. It is distinctly possible, because, I mean, I'm sure you're more brilliant than I am, because I'm not that smart. But I can tell you that if I can think up something, there are people who are always way smarter than me who have already thought about it and probably solved it. That's what I find most of the time. The hardest part about getting a PhD is coming up with a question that somebody else hasn't answered seriously. And then you end up with something that, once you're done with it, you look at it and you go, really? That was it? You came up with this little tiny itsy bitsy observation that nobody else had made before? They give you a PhD for that. So you're on the track. You're asking the right questions. I have no idea. I've never looked for that, but my guess is that somebody has explored that space, because almost everything has been. But that doesn't mean they've explored it in all the possible ways that could be explored either. You could look at it. My goal here isn't for you to build your PhD thesis. My goal here is to help you learn how to tackle the problems, how to design potential solutions, because that's what you're going to get paid the big bucks for. Eventually, you're going to have this skill set where people will come to you with problems that you look around and you go, nobody's tried to do exactly this before. And you're going to have this nice tool chest of things that you're familiar with, and you're going to start reaching in there and saying, not that one, not that one. Maybe this fits, but it's not quite right. So here, I'll file the edges off of it and I'll paint it green, and then I'll use it, right? Because every single one of these distributed systems ends up being bespoke. We've got lots of tools in the tool chest. You end up using them in slightly different ways, in slightly different combinations. I mean, look at Paxos. We've got Lamport with Greek legislatures and all of contracts and whatnot, and then he goes on to proposers and proposers, acceptors, learners, and then he does multi-Paxos, which is sort of iterating over more than one decision, and you get the PMMC people going in there saying, we're going to have a strong linear log, serialized log. We're going to give you a strong serialized log that's going to be replicated everywhere. And then the RAFT people go, well, it's kind of hard to understand. So here, we're going to give you a slightly different approach to this. And their actual log implementation is interesting in that they're isomorphic, but they're not identical. And you look at that and you say, these are all equivalent, but they're different implementations of exactly the same basic protocol. And then I point out that there's this big lie here, which is, yeah, and you got to do recovery too. Nobody does recovery the same. In essence, the reason we have different logs and different styles of logs is because they all solve the recovery problem slightly different. And we add optimizations in there because, of course, we're trying to make this thing run as fast as we possibly can. You end up with these optimizations, but you then say, the optimization isn't the protocol. The optimization is a way to achieve requirements of the protocol, but to do it in a way that minimizes the number of messages we have to send around. PMMC actually sends copies of their undecided decision in their election, in their ballots. They're trying to elect the leader. They actually send back their portion of the log that hasn't been decided yet. And that allows the new leader to catch up fairly quickly. But when you look at that, you realize that even in that case, the leader may not have enough information. So you still have to have strict Paxos level recovery protocol where the whole mechanism for deciding what you're missing. And RAFT does its recovery of the log slightly different again as well. It's the recovery that turns out to be hard. We thought that it was actually getting this linearization that was hard. Nah. Catching up the leader is a hard problem. And it's really easy to get wrong. Look, that's what the GitHub people up, right? Oh, we got split brain. We have a nice RAFT implementation that ends up with 2 leaders in different partitions. Wait a minute. Time out. I think one of our invariants was only 1 leader at a time. Can't get 2 quorums. If you can get quora. If you can get quora in 2 different partitions, your protocol is broken. So now you know what the invariant should be, right? And you put that, you go back and you say, really, and this is what happens now. You go to Amazon to work on this stuff. You go to Google to work on this stuff. You go to Microsoft to work on this stuff. Oracle, IBM, pretty much anybody. They're using modeling tools now, precisely because they want to make sure that your model for the implementation works. What works means that it obeys the invariance. You really have to kind of think about, what do I know is always going to be true? Kind of means you have to understand the problem that you're solving. Hence, back to what I said at the beginning. Pick the problem. I don't know if I answered your question or not, but I at least distracted you. And everybody else is falling asleep. They're thinking, no, for dinner. I mean, I love the costumes. You guys really went all out to dress up for Halloween. Thank you. It's very scary. And you look like UBC undergrads, which is very scary. I don't know. There's some yes people too. They would. Is that an undergrad degree, or is it like I needed a CS degree back on? I'm not sure. I went to a school that didn't have a computer science major when I was there. That's why I'm a math. Any other questions? Well, we're done. See you on Thursday. Same time, same bad channel, same bad jokes, different t-shirt. Have a good Halloween.